set up from the current slide. Got something for me? Good deal. Thank you. Okay. Okay. I got you marked. So, only announcement I know about, well, two. One just happened last hour, or last class. First of these, Alabama A&M is running the North Scholarship Program. It's a National Science Foundation grant, and the whole purpose is to encourage people to consider teaching math and sciences in the K-12 area. So please consider that. And be patient, right? All right. So I don't have any more information. It's all online. I mean, it's all out there. You got the email just like I did, so you can click on the link, read about it. It's a great program. It sounds like pay all your tuition and fees your last 2 years of school. Not bad. Not bad at all. So check out and see if that's correct. That's what I understood from another student who did look into it. He said that's what it sounded like. Now, the email that the vice president said something about internships, too. The guy who was looking at it on his phone, and I'm sure he couldn't read the whole thing there, he said he didn't see anything about internships, but he may just not have looked in the right places. So check it out, see what's there. It's well worth the effort. Okay. Any questions? Anything we've done so far? All right. Oh, one other announcement. And this just came up, like I said, the last period. Because I was out on Tuesday for that first class, missed the whole class, because I had to be at the lab by 7:40, and I was there before then, and then I was out the entire time. So they missed their whole class, and we decided to make up that class tomorrow morning at 8:30. And I'll be in this room 8:30 to 9:45. Okay? So, y'all want to make up yours too? I'll be right after. I'll have the book and everything here. I'll be here. No takers? Oh, I guess not. Okay.
I have a class tomorrow morning.
So I get.
I have a different class tomorrow morning.
Oh, okay. Yeah, likely. Yeah. Okay, good. All right. Let me get. Is it? Aaron. Huh? Ariel, got it.
I got to go to work tomorrow morning.
You pay much salary, right? That's the only reason you do, right? Okay, good deal. All right. All right, so I will not be on the whole purpose of saying that. Normally on Fridays I have office hours on the Birmingham campus from 8 to 12. Not tomorrow. Tomorrow I'll be here on this campus. I will be here probably before 8 o'clock in the morning, but I'll be in this classroom from 8:30 to 9:45, and then I'll be back in my office after that. Now, I don't know that for a fact either. I've got to call and talk because the class just decided, earlier that, so I will be, call my boss today and see if there's any reason I have to go back to the Birmingham campus. If not, I'll just work here all day tomorrow. But if he said, no, we got a meeting or something else like that, then I may have to go back to the Birmingham campus. So I'll find out tomorrow. But as far as I know, right now my preference would be I'll be on campus, on Bessemer campus tomorrow rather than Birmingham. And I've got to contact my Math 126 independent study students and let them know I'll be here and not there because they usually come out there. Okay. Is it Cynthia? Huh? Okay, a little louder. Ennis. Got it. I just got to find. Oh, there it is. Jemiah. Okay. I was looking for I-N-N-E-S, not E-N-N-I-S. Okay, got it. All right. So, in case you didn't hear that, tomorrow, normally on Fridays, I'm on the Birmingham campus, 8 to 12 for office hours. Tomorrow, because I'm making up the class that I missed on Tuesday because of my doctor's appointment for my 112 class, I'll be here in this classroom, not down there, but in this classroom from 8:30 to 9:45. So before 8:30, from 8 to 8:30, I'll be in my office downstairs, And then after 9:45, I'm hoping to just continue working here on this campus. But if we have a meeting or some reason I have to go to Birmingham, then I'll have to go to Birmingham. So I'll be at one or the other after our makeup class tomorrow. All right, any questions? All right, we almost finished 4.6. All we got is a little bit of a summary here to go. And below is a summary of the characteristic of the 6 basic trigonometric functions. Sine function, okay? Now this is just pure old plain and simple sine x. Amplitude 1, b is 1, period 2 pi, regular old, no phase shift, no vertical shift. It's a periodic function, stays between plus or minus 1 on the y. It's periodic, it's a period of 2 pi. It starts at 0 and continues up from there. So here's Caitlin, right? And Lee, but I gotta find you. There you are. Right there. All right, anyone else coming since I called roll? Okay, the only major announcement that I have that might pertain somehow. Normally I have office hours tomorrow, Fridays on Birmingham campus, West campus from 8 to 12. Not tomorrow. Tomorrow I'll be here making up a class for my 112 class because I missed it Tuesday because of our doctor's appointment. So we'll be here in this room from 8:30 to 9:45. So from 8 to 8:30 I'll be down in my office here on this campus, and then after 9:45 I just found out now that they wanted to do this. So Demetric is here. Okay, let me start that announcement over with. Normally on Fridays I have office hours on the Birmingham West campus from 8 to 12. Let me start over a minute. Okay. Well, the prodigal returns. Okay. Jake is here. All right. Good deal. All right. Okay. For those who didn't know, last Tuesday I had a doctor's appointment, and it wiped out my 8:30 class completely. I mean, I had to be in the lab by 7:40. I was there actually early, and I thought I'd be back on campus by 10. I wasn't. It was 10:30, so my 8:30 class was completely wiped out. We decided today they chose to make up the class tomorrow morning from 8:30 to 9:45. So whereas normally on Fridays I'm on the Birmingham campus, West campus, 8 to 12, tomorrow I will be here from 8 to 8:30 down in my office, and then in this classroom from 8:30 till 9:45. Now after that I don't know where I'll be. I've got to call and talk with my boss today and see. I know I've got to go to the Birmingham campus sometime tomorrow because I have to do a travel request because I'm taking my physical science class on a field trip next week, and I've got to do a field trip request form, travel form, all that kind of stuff. So I've got to go there sometime, but I'd rather do it just on my way home. But if I need to be over there for something else, like a meeting or something, then I'll go over there sooner. So I don't know how long I'll be here. I know I'll be here till 9:45. Okay? So, any questions? All right, where we were before some of you came in, we were talking about the basic trigonometric functions. Here's the first 2 of the 6. Here's the sine function. Starts at 0, period of 2 pi, range plus or minus 1, periodic function, continues domain everywhere, all real numbers, and it goes up and down like this. Smooth, continuous function, maximum of pi halves, intercept at pi, minimum at 3 halves pi, and then back to pi, and repeats itself or repeats itself. Period 2 pi. Cosine function, almost identical. The only difference is if you take the sine function and move it back pi halves, okay, then you have the cosine function. It starts at 1, goes down to 0 at pi halves, down to minus 1 at pi, and then continues back to 1 at 2 pi, and continues ad infinitum. So again, domain all real numbers, range again between plus and minus 1, period again of 2 pi. It's just the starting point is different from the sign. The shape is identical. Everything is identical except where it begins. Okay? Pretty simple, right? We can graph. And what does an amplitude do for us? Second? Yes, that will expand it as either a vertical stretch or a vertical shrink, depending on if that A is less than 1 or greater than 1. Okay. What would a B do for us if you had something in front of the X here? What would that do for us? Changes the period. How does it change? A large B greater than 1 will actually be a horizontal shrink. A small, like less than 1, between 0 and 1, that would be a horizontal stretch. Remember, anything that's happening to the X is always backward from 1 to 3. Okay? C, something added or subtracted from the X, is going to be a phase shift, a horizontal shift, one way or another, right or left. And again, if it's a minus, it's going to the right. If it's a plus, it's going to the left. And then finally, if you had a D added on to all the things, that is a vertical shift. If it's a plus, it's going up, and minus is going down. Same thing for cosine. Okay. So we know how to graph sine and cosine. All right, now your tangent and your cotangent functions, and all the rest of the trig functions, have vertical asymptote because they all are defined as ratios. And the ratio will be a sine or a cosine, okay? And since the tangent is a sine over cosine, everywhere that cosine was 0, you have a vertical asymptote. Remember, your cosines were 0 at the half pi's, all right? So every half pi, your tangents are vertical asymptotes. Not defined there at all. In between the vertical asymptotes, you'll have a 0. And in between the 0 and the vertical asymptotes, you'll go minus A to plus A. If this is A is 1, from minus 1 to plus 1. And that would be at pi fourths. Because the period for tangent and cotangent, their periods are pi. The other 4 are all 2 pi. Tangent and cotangent are pi. Okay? So domain, all real numbers except those half pi's. And range now is negative infinity to positive infinity because tangent keeps climbing, going toward the vertical asymptote but never reaching it, or it keeps going down on this side toward the vertical asymptote but never reaching it. Okay? Cotangent function. A lot like the tangent, except it's 1 over tangent. So everywhere tangent is 0 or sine is 0, you have a vertical asymptote for cotangent. And everywhere that you had a vertical asymptote for tangent, that you have your 0 for your cotangent. Or in other words, where the cosine was 0, you have zeros for cotangent. Where the sine was 0, you have vertical asymptotes for cotangent. The sine is 0 at the whole number of pi's. Okay? Minus pi, minus 2 pi, minus 3 pi, 0 pi, pi, 3 pi, 2 pi, 4 pi, 18 pi, whatever. Okay? So the domain, again, is all real numbers except for your n pi's. Range is all real numbers, and the period is pi. Okay. Any questions on tangent or cotangent? Okay. Sort of a trivial kind of question here. Which 2 trig functions can have values in all real numbers? Only these 2. Because sine and cosine are stuck between plus and minus 1. And secant and cosecant are restricted from plus or minus 1. Okay? Tangent and cotangent, any real number could be in the domain. Okay. Now, moving on to the last 2, the secant and the cosecant. They do cosecant and secant. Remember what they're reciprocal functions. Cosecant is reciprocal of sine, so everywhere sine is 0, vertical asymptote. Just like it was for cotangent, okay? Because cotangent is cosine over sine. So again, everywhere the sine is 0, since sine starts at 0, It's 0 here, that's a vertical asymptote, and then again at pi, 2 pi, 3 pi, 4 pi, negative pi, all like that. Okay. To draw these, actually first draw the sine function in here, and then have them kiss at the max and go in the opposite direction, kiss at the min and go in the opposite direction. And again, you see now the period is 2 pi, not pi. Pi was only tangent and cotangent. So the main all real numbers x except your n pi's, just like it was for cotangent. The range is only between negative infinity and negative 1, including negative 1, and then 1, including 1, to positive infinity. Nothing in between. Okay? Period 2 pi. Identically the same thing for cotangent, except, secant, except for it's shifted. Okay? Just like cosine was a shift of sine, secant is a shift of cosine. So if you just take this thing, move it pi halves this way, you got the secant function. They look identical except for where they begin. This begins at 1 and goes up to there. It's vertical asymptotes are your half pi's because it's for cosine 0, just like tangent was. So the main all real numbers except those half pi's, and the range again just like cosecant was, negative infinity to minus 1, including minus 1, positive 1 to infinity, including positive 1. Period 2 pi, just like sine and cosine. Got it? And that is the last. Okay. So I guess we'll go to the last. Let's do the vocabulary here. The tangent, cotangent, cosecant functions, they left out secant, are blank, so the graphs of these functions have symmetry. Oh, I see why they left it out. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to blank. How are tangent, cotangent, and cosecant different from secant? Okay, there's secant, there's cosecant. There's cotangent, there's tangent. These three, these two, plus the first one here, have one thing in common, and secant has another, is different. What would that be? Hint, symmetry. Symmetry with respect to, what about a function that determines its symmetry? Okay, this is symmetric about the origin. This is symmetric about the y-axis. What feature of a function determines that? Odd or even, which is which? Let's go back to the first question. Hang on to that. The tangent, cotangent, and cosecant functions are blank, so the graphs of these functions have symmetry with respect to the blank. What are those three? No. So there would be odd. Okay, 1 out of 2. Okay. All right. They're odd because this has symmetry with respect to the origin, right? This has symmetry with respect to the origin. What it's doing up there, it's doing down here. They're odd functions. The f of x is the same as f of minus x is the same as the opposite of f of x. Odd functions. And so is the cosecant function. What it's doing down here is like that. F of minus x is minus f of x, the opposite of that. Whereas, well, wait, let's do the next one. So what do they have symmetry with respect to? So the first part of 1 is odd, and the second part they have symmetry with respect to the, I've said it about 3 times, origin. Excellent. Number 2, the graphs of tangent, cotangent, secant, and cosecant functions have blank asymptotes. Vertical asymptotes, perfect. No horizontal asymptotes here. To sketch the graph of a secant or cosecant function, first make a sketch of its blank function. Second, or reciprocal. Yeah, reciprocal function. When you say inverse, that could be inverse cotangent. Yeah, they could open a different bag of worms. So reciprocal function. Okay, number 4. For the function f of x equal g of x times sine of x, g of x is called the blank factor. Last thing we did last time. Damping functions, exactly, or damping factor, okay? The period of y is equal to tangent x is blank. Period of y is what? Pi. Perfect, okay? The domain of y is equal to cotangent x is a set of all real numbers such that x is, I'll put that part in. Domain of y is equal to cotangent x is all real numbers such that x is what? Or not what? Help me.
X is not n to the pi.
Yes, the cotangent would be not an odd pi, a half pi. Cotangent. Wait, did I say it right? No, not a pi, a multiple of pi. You're right. Multiple of pi. Such that x is not a multiple of n pi. X is not n pi. Number 7, where n is an integer, by the way. The range of y is equal to secant x is blank. The range of y is equal to secant x. Oh, let's get this off the air. It's the range of secant x.
It can be anything but in between -1 and 1.
Exactly. So it would be from negative infinity up to -1, counting -1, and then picking up again at +1 and going to positive infinity. Perfect. Okay, the period of y is equal to cosecant x is 2 pi. Excellent. All right, homework exercises here. You've done most of them before, but let's just pick them up. I would do all of 9 through 14. It's just matching the graphs with the functions. Only the odds have the answers in the back and also at calcchat.com, but you should be able to match all those. Then do any of the odds 15 to 37. They're all at Calc Chat, 19's at Calc View. Do any of the odds 39 to 47. They're all at Calc Chat. Do any of the odds 49 to 55. They're all at Calc Chat. 51's at Calc View. Do any of the odds 57 to 63. They're all at Calc Chat. 57's at Calc View. Do either 65 or 67. They're both at Calc Chat. Do either 69 or 71, they're both at Calc Chat. Either 73 or 75, they're both at Calc Chat. Either 77 or 79, they're both at Calc Chat. Then, applied problems, you can do any of the odds 83 through, or 85 or 80, 83 or 85, they should both be at Calc Chat. All right. Devin, right? Believe it or not, I have 2 Devins. One's Monday, Wednesday, one today, but y'all spell them differently. So I always look and say, wait, that is the right spelling here. Okay. All right, we're doing I was just making assignments for 4.8. We just finished, 4.6. We just finished 4.6. I said do either 83 or 85. They're applied problems. They both should be at Calc Chat. Then there's some exploration. 87's a true false. You won't see one like that on the test necessarily, but it's good to think through. You can think about doing 89 if you'd like. Same with 91. That's a graphical reasoning problem. And then 93 is another graphical reasoning problem. You can do that if you choose. So let's move on to 4.7. Didn't have much of 4.6 left to go, so let's go to 4.7. Any questions so far? Any questions? Oh. must be. Let's see. All right. And anyone else come in that I didn't see? I didn't call you that. Okay. All right. We're ready to go with this then. Slideshow to current slide. Still in Chapter 4, almost reaching the end of it. 4.7 is inverse trigonometric functions. And this is why we didn't want to call that to the minus 1 and inverse. We want to call it reciprocal. Those are different. So our objectives here in this section are to evaluate and graph the inverse sine function, evaluate and graph the other inverse trigonometric functions, and then we'll evaluate the composition of trigonometric functions. Because that's something you'll be doing in calculus. And hopefully all of you, most of you will get there. All right, inverse sine functions. We know, hopefully you know this, for a function to have an inverse, what has to be true about it? Medium one-to-one function. What do we mean by that? Well, to be a function, for every x, there's one and only one y, right? For a one-to-one function, still is a function, so for every x, there's only one y, but then also for every y, there's only one x. One-to-one. One-to-one. Okay? And that means for a function, it has to pass the, I'm not blessing you or anything, the vertical line test. To be one-to-one, it must also pass a horizontal line test. Y'all remember that from pre-calculus algebra? I can tell you do, okay? So it's like, it has to be a one-to-one function, and it must pass the horizontal line test. Now, from this figure here, this is a good old sine function, right? You think it's a one-to-one function. What you think? Think the line here is going to pass it only once? No. It repeats itself forever and ever and ever and ever. So therefore, not every horizontal line, in fact, every horizontal line between minus 1 and 1 is going to have an infinite number of intersections. So it's not going to work, is it? So therefore, can we not have an inverse sine function? We can only if we restrict the domain of your sine function to say between pi halves and negative pi halves and pi halves. In this portion, not this portion only, but in this portion, that is a one-to-one function. Horizontal line test passes, vertical line test passes, everything passes. It's one-to-one. Now the other way to talk about this, and the book seldom says it, if it's a continuous function, it has to be monotonic, meaning it has only in one direction, either strictly increasing or strictly decreasing, one or the other. So if you chose this to be it out here, that is one-to-one if you choose from here to here, because it's strictly decreasing there. Same here. Here it's strictly increasing. Monotonic, one-to-one, it means basically the same thing. Okay. So normally the y is equal to sine x doesn't unless you restrict the interval, your domain. Okay? And then it does have an inverse sine in this domain. And in that domain only. Well, once you pick that one, you can't extend it any, because anything else that you do here is going to start failing horizontally. It will no longer be one-to-one. Okay. However, when you restrict the domain to the interval minus pi halves to pi halves, and notice here you include the endpoints, because there's no turning back yet. You might pass that and turn back, but not yet. Corresponding to the black portion of the graph we just saw, these properties hold. On that interval, including the endpoints, negative pi halves to pi halves inclusive, the function y is equal to sine x is strictly increasing. That was that monotonic, strictly increasing. On that interval, y is equal to sine x takes on its full range of values between minus 1 and 1. So don't make the domain any smaller because you won't take on the full set of values. And on the interval minus pi halves to pi halves, y is equal to sine x is 1 to 1. Because it is strictly increasing. Because it is, does take on all its values. Okay? Meets those criteria, it's got an inverse. It's a 1 to 1 function. So the restricted, on the restricted domain, minus pi halves to pi halves, and this is just what convention has. This is the part that we'll do. We're not going to do that part here or the part over here. We'll do this part right here, minus pi halves to pi halves. Y is equal to sine x has a unique inverse function, and we call that the inverse sine function. And it's denoted by, in my mind, this was the old way of referring to it, arc sine, or inverse sine. Okay, now this is why, we'll talk about this in a minute. This author loves arc sine more than he does inverse sine. To me, inverse sine is, I don't know, it's easier to write. This whole thing is shorter, but I don't know why he uses arc sine so much. Okay, both of those mean the same thing. Okay, and what does this not mean? Reciprocal. If that were a number or a variable, that would mean reciprocal. But with this being a function, just like f or g, if that's the name of a function, you have that line, it means inverse function. Does not mean reciprocal. X to the minus 1, that means 1 over x. 7 to the minus 1, that means 1 over 7. Okay? But that is consistent with this notation, f inverse. That means inverse function, not reciprocal function. Now, the arc sine of x comes from the association of a central angle with its intercepted arc length of a unit circle, and that's why they call it the arc sine. Now that to me is not very satisfying, but I guess that's where it came from, okay? So to me that's sort of, do I think of that every time I see inverse sine? No, I think of what it means. So arc sine x means the angle or the arc whose sine is x. Okay? Now, that is getting down to really what we are dealing with. Here, now, the book doesn't emphasize this, and I guess most mathematicians don't like you to even think this way, but to me this makes sense. A trig function operates on an angle. Now, if that angle is in radians, it doesn't have a degree or anything with it, it's just a ratio. It's just a real number, but that's still an angle, some angle. That's what it's referring to. And it operates on that and gives you a number. 0.973, negative 0.621, 0, whatever. It's just a number. It operates on an angle, giving you a value of a number. If you do the reciprocal function, this is the number, that's the angle. This is the number, that's the angle. Now, again, the angle doesn't have to be degrees, it may be radians, but that's, to me, helps me keep it straight what's what. Okay? So, that's why they say that the arc sine of x means the answer here is an angle. The angle whose sine is x. So that's the number, whose sine is x. Okay. And that's going to be, I think, helpful in everything you do with inverse sines or arc sines. Okay. Both notations, arc sine and inverse sine, are commonly used in mathematics. So just remember that inverse sine of x, meaning the minus 1 there, denotes the inverse sine function rather than the reciprocal kind. Because what's the reciprocal sign? Which is? Has a different name. So, someone say it? Cosecant, yeah. We don't need this different notation. We know what 1 over sine is. It's cosecant. So inverse sine and inverse any function, the minus 1 there means inverse, not reciprocal. Now, the values of arc sine x lie on the interval from minus pi halves to pi halves, because these are the angles that we defined the inverse sine over. So when you take the inverse sine, you switch your x's and the y's. So these become your range. They're the domain of the sine function. They're the range of the inverse sine or the arcsine function. What would be the domain of the arcsine function? Not that hard. If the range of the arcsine function is the domain of the sine function, right? Minus pi half to pi half. That's the domain of the sine function. It's the range of the arcsine function. So what would be the domain of the inverse sine function? Minus 1 to 1, which would have been the range of the sine function. Exactly. Okay? And there you see it. Okay? So here's what the graph of the inverse sine of the arcsine of x is. Okay? Now, number one, flip your numbers. Again, sine goes from minus pi halves to pi halves, and the range goes from minus 1 to 1. So flip those over so that the domain of arcsine is minus 1 to 1, and the range is minus pi halves to pi halves. Now, here's the other thing I remember, and it helps me get it closer to right. Let's go back to the sine function. There it is. Okay? Notice what the slope of the sine function is here. It's approaching 0, right? And here it's approaching 0. The endpoint is approaching 0. Sine function does that, right? Now, what would that mean for the inverse sine? If you're, oh goodness, what happened? Is that where we were? No, that's where we were, okay. All right. Now these are approaching vertical. The other was horizontal, these are near vertical. So actually, they don't have slopes there. It's going to infinity. It's getting steeper and steeper and steeper downhill, steeper and steeper uphill. So that's the other thing I remember about the inverse sine. The slopes are not going to 0, they're going to near vertical. Okay? That helps me with the graph.
You said that was for inverse?
Huh?
That was for the inverse?
Yeah, the inverse sine. Yeah. And then the other thing I think I found sort of helpful is this. Let's go back to the sine function. Notice here, I pointed this out to you before. Real close to the origin, that's almost a straight line there, isn't it? Almost the identity function. 1 to 1, right there. You know, almost the identity function. So therefore, when you reverse the axes, whoops, too far. This is again almost a straight line, right near the origin. Okay, and it's exactly the bisecting line. You know, the 45. You know, right there. Okay. The difference is for the sine, the curvature is like this and like this. For the arcsine, it's like this. Make sense? And of course, the ranges and domains are reversed. All right. So here's the definition of the inverse sine function, or the arcsine function. Defined this way: y is equal to arcsine of x if and only if sine of y is equal to x. That's just what I was saying. Sine operates on an angle giving you a number. The inverse sine operates on the number giving you the angle. So this is true only if sine y is equal to x. So in other words, if you took the sine of both sides of this, this would give you sine y right there, and the sine of an arcsine, that's the angle function times its inverse. They disappear and just give you x. Okay? That's what inverse functions do. When you pick a number, any number, 2, add 4 to it. and then subtract 4 from it. 2, you get right back where you started, right? When you do a sine of an arcsine or arcsine of a sine, as long as they're defined, then you get right back to what you started with. X. And that was how we defined or tested inverse functions. Because when you did the inverse and the function on the same quantity, you wind up with x. Okay? Now, the difference here is the domains. The x here has to be between -1 and 1. It can't get outside that because it can't get outside of it here. But the y has to be between -pi halves and pi halves because that defines the whole range here. Okay? Because that's where your arcsine, your y's go from -pi halves to pi halves. So the domain of y is equal arcsine of x is -1 to 1. The range is -pi halves to pi halves. Inclusive on both of those. Exactly the opposite of what it would be for y is equal to sine x. Then the range would be -1 to 1, and the domain would be -pi halves to pi halves. Make sense? All right. So, if possible, find the exact value. The arcsine of -1/2. Now, here's where I pull in my little saying, and if you don't like it and don't like to think this way, think the way the book does, okay? But here's what I think, okay? Let's just say this is equal to something. Whoops, let me get my pen back. Okay. Ah! It didn't shake. There we go. Okay. Equal to something. Do you have anything you want to name that something? If you had to choose anything in the world to name that, what would you name it?
Like a variable?
Yeah, like a variable. Okay. No favorite variables. Here's my favorite. Okay. This is going to be a something. I'm not going to fill in the blank yet, but it's going to be something. Now, tell me what kind of a number it is. What kind of a number will that be? What will you be measuring with that number? I didn't like the way I described it. Okay. I'll give you my variable. One I like to think of it as. I like to think of this as theta. Now, why would I choose theta and not x? I knew that's what Christian really wanted to say, but he wasn't going to say it, right? Yeah. I could read your sick mind. I mean, never mind. I shouldn't go there. Okay? Now, why would I name it theta as opposed to x? X is everybody's favorite, isn't it? Say again? Because it's, well, actually, it's an angle. Yeah. Exactly. Because what does this mean? Arcsine of -1/2 equal theta. Can you give me an equivalent equation, but not using an arc? An equivalent equation to that, just change a few things around. Sine of theta is equal to -1/2. That's why I chose the theta, because that represents an angle. That plants it in my head. I'm looking for an angle here, an angle whose sine is -1/2. Now, remember where we're limited, because arcsines, sine is not limited anywhere, but arcsines are. So that means you have to limit the theta between what? -pi halves and pi halves. You're absolutely right. Okay? So, in between those two, what would theta have to be here? What angle theta gives you a sine of -1/2? what angle theta would give you a sine of 1/2. Don't tell me you've forgotten your favorite angles already. They're going to be hurt. 30 degrees or pi over 6. Pi 6 radians. Or 30 degrees. That's perfectly fine too. Okay? But in calculus, most of the time we stay with radians. Okay? Oh, that is theta if it was positive 1/2. This is negative 1/2. So what would that mean? Negative 30 degrees or negative pi 6. Notice here we now start using negative angles. Why? Because look at that. You're restricted to those angles. Negative pi halves to pi halves. You can't do, that would have been 330 degrees or 11/6 pi. Don't use those, okay? They're outside the domain or range, whichever you happen to be dealing with, okay? So that would be minus pi 6, okay? Does that make sense? Does that help you see what the answer sort of has to be? To rewrite it in terms of sine, cosine, or tangent, or whatever you're dealing with, rather than the inverse tangent, which you go, oh, now wait, which, you know, to me, I'm familiar with this, that should give me an answer. Now, if you haven't learned these, then maybe it doesn't matter to you, but I'd say learn them, okay, get to know those angles. All right, how about that second one? What would you do with that? I love it. Set it equal to some variable, and why not have one that makes you think angle, theta? Okay, alpha would work too, okay? And then rewrite this. What would that be rewritten as? Sine of theta is equal to square root of 3 over 2. And then within the confines of where the angles we deal with, what angle theta would that have to be? Pi thirds. So this would be theta is equal to pi thirds. Okay. All right. How about number C? Why not? Yes, because that's outside the domain of inverse sine. Inverse sine has to stay between -1 and 1. So D and E does not exist. I see this, a lot of students doing that. Sometimes I'll think, 1? Why did they write out 1? That's not the answer. No, if they're sloppy. Okay. Does not exist. It cannot exist because there is no angle. And if you wrote it and said, well, let's let that equal theta or whatever you want to call it, then the sine of theta is equal to 2. It can't be. Sine of theta is always between -1 and 1. Never 2. Never 1.1. Never. Okay. So let's clear my scratch out of the way. Any questions on this before I clear it? Okay. So on the first one, and this just gets me. Well, because this is true, then that has to be the answer. Okay. To me, that's sort of like, well, if I knew that, why would you ask the question, you know? But it's just saying the same thing we did, only it's sort of doing it backwards. I say, name that, and then rewrite that. Sine of theta is equal to -1/2, and then figure out what theta has to be. So, to me, this is really close to what I consider circular logic. Because this is true, that's true, you know? Right? Okay. But also, the other part is that answer has to lie between -pi halves and pi halves, because that's restricted, in this case, range, okay, that you have for an inverse sine function. Now, I like doing it my way, because this way, it just seems like you're running in a circle. And if you do it the other way, yeah, you probably are still running in a circle, but at least you're having to think your way around the circle. And then they do the same thing here. Well, because this is true, that's the answer, okay? Well, yeah, but how did you get that? How did you get that to be true? Well, give it some name, theta, then the sine of theta is that. What theta does that have to be? Well, it has to be pi thirds. Yeah, you did the same thing, but you don't start out acting like you knew the answer before you started. Okay, even though you may have. But pi thirds also has to be in between, in that range. Any questions? Again, you can tell I don't really care for the technique here. That's why I gave you the other one. And then the C, it is not possible to evaluate that with x equal 2 because there is no angle whose sine is 2. Assign a value theta, just like, or they assign it y, that would be fine too. There is no angle y whose sine of y is equal to 2. Remember that the domain of the inverse function is minus 1 to 1 because that's the range of the sine function. All right, here's example 2. Sketch a graph of this one. So, I'm going to draw a vertical axis and a horizontal axis, but I'm going to ask you to help me label those axes. What would be good labels for your horizontal axis? X. Now, here again, I like to think in terms of what kind of quantity are we dealing with. What are your x's? And what are your y's? Which was between negative 1 and 1? Second? Nope. One or the other. Which? Second?
Just the x.
The x is between minus 1 and 1. Whoops. Okay. And what's the y between?
Pi halves.
Negative pi halves and pi halves. Okay. And why is that? I go and say, well, I want to rewrite this as an equivalent equation. And that would be the sine of y is equal to x. And I know what you take the sine of y, what you take the sine of, you take the sine of angles. Well, these measure the angles, minus pi halves to pi halves. And your x then are the numbers, so this has to be minus 1 to y. That's how I do it with my little mind, so you do it however floats your boat. Okay, so we got the axes labeled. We haven't sketched a bit of the graph. So you're going to have to give me some points. And frankly, I don't even think in terms of arc sines or inverse sines. That's why I wrote the other one up there. I do think in terms of that. When y is 0, what is x? Also 0, okay? We got a first point, okay? Now, what's another point that I could pick out a y and know what the value of x would be? Pi over 2, when you said 2 or 6? 6, okay, pi over 6. Pi over 6 would be about 1/3 of the way here. So this would be pi 6. And this will be pi thirds, okay? And when y is pi 6, what is your x? Sine of pi 6 is 1/2. Well, that would be right here. So that would be this point right here. Okay, we got another one. He likes to work really hard, I can tell, okay? Any others?
You can do the negative, right?
Second?
Can't you do the negative?
Okay, yeah, we can do that. So that would be negative pi 6, and that would be negative 1/2. Why can we do that? Because sine is an odd function. It's the opposite of it, okay? So that would be this point down here. You can do pi, I like pi halves. What would its value be? 1. So that would be right here, sort of. Okay? And? Second? negative pi halves and negative 1. Now, I've got the points in there. Here's the other thing I think, okay? The sine function I know is smooth and horizontal at those endpoints, right? So these are smooth and vertical at the endpoints. So you start by going up from here, through here, and up to there. Make sure those are going to vertical tangent lines, not horizontal ones. There it is. Nice to have those other 2 points in there, but I usually only do the endpoints. So then, because I don't have another one to head toward, I just have to remember this is vertical, that's vertical. So once you get it going right near the origin, you're the diagonal line, almost a straight line. Okay? Make sense? Okay. Let me clear this out of the way so you can see what they do. Though I can't imagine it's any better. Can you? Say no. Okay, good. Okay, y'all get brownie points today. By definition, the equations y is equal to arc sine x is exactly equivalent to sine x is equal to y. I mean, sine y is equal to x. I always write down that equivalent equation because I think in terms of sines. I don't think in terms of arc sines. So I rewrite it that way, and the y's are going from minus pi halves to the x's are going from minus 1 to 1. So the graphs are the same, but now you just have to graph them on the, flip your scale, your axes. So if you like to do a table, do a table. And here they did. They did the pi 6, and I like those. I don't like these as much because I don't think in terms of square roots of 2's, okay? But, by the way, square root of 2 over 2 is approximately 0.707, okay? Because square root of 2 is 1.414, and so half of that would be 0.707. So I can think in terms of those. The pi thirds and square root of 3 over 2, I don't think in those terms at all. You can do them on the calculator, okay? If you like to do tables of values, do them. I just like to pick basically 3 points to do them. This, that, and that. How about I know those? These 2 are fine too because I can approximate those, okay? And then fill in the blank. Connect the dots, okay? And again, notice you have vertical asymptotes for the inverse sine function, not asymptote. Vertical slopes here and here are almost vertical, and you have your almost 1-to-1 slope there. Make sense? All right. Note that it is a reflection across the line y is equal to x of the black portion of this. And let me point the things out to you I just said. Notice this is a near horizontal slope here and here. That makes the other 2 vertical. Of course, your scales swap on you. But the other thing is, look at this. That is almost your y is equal to x right there. So it's no surprise when it reflects across y equal to x, it's still almost y equal to x. But that's the part that helps me get the middle part right, close to right. And by the way, there is no more inverse sine. That's all she wrote, okay? You can't have another input beyond 1. There's no value there. And you can't have another output beyond pi halves or negative pi halves. That's it, folks. That's all. That's all the inverse function is. Well, that's only covering from minus pi halves to pi halves. What if you had an angle over here in the second quadrant, or the third quadrant, or the fourth quadrant? Okay, well, second quadrant you have, no, I'm sorry. First, let's see if I get it right. From minus pi halves to pi halves, the second or third quadrant. You have fourth quadrant, second or third. What if you have an angle over there? You're not going to get that as a result here. You cannot get that as a result. If indeed that's where you were living and you fed in a value, remember because the sine is an odd function, you can just add 180 degrees of pi to it, and you'll get, or actually subtract from, or add to it. If you got an answer in here and you needed the angle over here, just add pi to it. Okay, that will give you the right result. Okay, we're not going to mess with that now, though. Note that is the reflection across the line y is equal to x of the black portion. Oh, we just said that. I guess they're going to show that. No, they're not going to show it. Remember that the domain of y is equal to arc sine x is the closed interval minus 1 to 1. The range is closed interval minus pi halves to pi halves. They've said it plenty of times, so I guess it's important. Okay. Now, was there an example 3? Oh, after each example there is a checkpoint. Please do the checkpoints. No, there is an example 3, but we haven't gotten there yet. So let's do other inverse trigonometric functions. Here's kind of the good news. Okay, we're going to do inverse cosine. Okay, it's a little more involved or stranger than sine, inverse sine, but we can live with it. And we'll do inverse tangent. But guess what? We're not going to mess with inverse cotangent, cosecant, or secant. No. Secant and cosecant get really bizarre. And I can't imagine many cases of ever wanting to use them. So we're going to stick with just these 3, sine, cosine, and tangent. So let's do cosine next. And here's a problem with cosine, folks. You can't use minus pi halves to pi halves. Why?
Because it doesn't start at the origin.
Well, it never does.
Yeah.
Why can't you do this?
Because then it would pass
The?
It's not a function right from right there.
It is a function, but it's not a, it won't pass a horizontal. Right, exactly. It's not a one-to-one function. It is a function, but not one-to-one. So we have to use a different interval. Now, we could have chosen this one had we wanted to, but I don't really care for negative numbers that much. So let's go positive here. There is the segment, the only segment we're going to use for the inverse cosine. Because the cosine has to be one-to-one on that interval. Now the domain of cosine is 0 to pi, inclusive, and the range is still minus 1 to 1, inclusive. Okay? So cosine has an inverse on that interval only. We don't define it anywhere else. Okay? It's 1 to 1 on that interval, so that's what we're going to choose. We're not going to choose this one or that one or any other. We're going to choose that one. Consequently, on this interval, the cosine function has an inverse function, the inverse cosine function, cleverly named, and they either call it the arc cosine or the inverse cosine. I like inverse. Okay? Both of those are the same, equivalent, and neither is any better than the other. I'll say it this way. The old calculators used to say arc sine and arc cosine over the keys. Most of the newer ones say inverse or cosine and inverse sine over the keys because it's easy to write, and they tend to put more junk on the keys too, so it's shorter and easier. Okay, but I guess you can find newer calculators that have the old thing too. I don't know. Okay, similarly, you can define inverse tangent function, but this time you restrict the domain to the interval minus pi halves to pi halves. Now, is that the same as sine? Yay or nay? Is that the same as we did for sine? Looks pretty similar, doesn't it? Is it the same? One tiny little difference. Sine included the endpoints. Why doesn't tangent? Second? Yes, and cosine is not cosine is 0 at the endpoints, so therefore tangent is not defined at the endpoints. So that's why you have to have parentheses there, not brackets. Sine, they are defined, so you could put brackets. Tangent, no, never has an answer there. So the following list summarizes the definitions of these 3 most common inverse trigonometric functions. Y is equal to arc sine x or inverse sine of x if and only if sine of y is equal to x. That's what I always do. Write the equivalent expression and then deal with this one. Okay? Domain of this, the x values are between -1 and 1 because that's what they have to be here. That includes the endpoints. The range is the y value here. That has to be between -pi halves and pi halves because that will give you those endpoints. And you include those. The arc cosine, however, and that's if and only if cosine y is equal to x, only defined on this domain for the arc cosine, -1 to 1, that's the same. The range shifts because to get 1 to 1, you have to be between 0 and pi for your y. Okay, included. Okay, but then the arc tangent or inverse tangent. The domain here is all real numbers because the range of tangent is all real numbers. Remember we said that. Tangent, cotangent are the only ones who have a range of all real numbers. Okay? Therefore, the domain of the inverse tangent is all real numbers. And if we did an inverse cotangent, which there is such an animal, but we don't usually use it, it would also be negative for the all real numbers. Okay? But the range of this, the y value here, now has to be restricted to -pi halves to pi halves, not counting the endpoints. Sine and arc sine included the endpoint, arc tangent cannot. Those are not included because it's not defined. Tangent of pi halves is not defined, or negative pi halves. Okay, does that kind of make sense? Oh, wow. We've got Ryan here today. Okay. Now, we're in section 4.7, and we're on right about the bottom of page 320. Okay? In fact, these are the graphs there. The graphs are the three inverse. We did this one in gory detail. Inverse sine, remember it's 0, 0, 1 pi halves, -1 minus pi halves. Okay? Remember it was nearly 1 to 1 here, and it goes into a vertical tangent there and a vertical tangent here. Okay? Because if you flip this like this, like somehow there, then you would have it going like this and like that. Now, arc cosine. This is harder for me to remember. Okay? Because, remember the cosine would be starting at 1 and going down like this, right? That pi halves over here, going to pi. It's just really bizarre. When you invert that, okay, your minus, before you started at 1, at 0, 1, here you start at 1, 0. This probably is the best way to remember. And then you move to pi halves 0, so now you go to 0 pi halves. And then you went to pi -1, so here you do -1 to pi. So you sort of have to just graph it backwards. Okay? And remember this, the slopes are going toward, the tangents are approaching vertical lines at the end here, just like they were here. So that sort of finishes your picture. Pick these 3 points, and then make sure your tangents are near vertical here and here. And this winds up being nearly the inverse 1-to-1 function, except to find an origin. So to me, that's harder to grasp. I have to stop and think about it. Here's the way, really, I remember. The first quadrant, everything's positive. So you have to be here, okay? And in the fourth part, the second quadrant of your cosine function, you're negative. Well, you don't, because the cosine will never have a negative value. This will never have a negative value down here. So you have to be going this way. Actually, you're going this way, but I think of it that way. Probably not. Okay, and then this arctangent or inverse tangent. The tangent goes like this, inverse tangent goes like that. Now they're horizontal asymptotes, not vertical asymptotes, and still very much like sine, right near the origin, you have always the identity function. Okay? And whereas tangent function is approaching your vertical asymptotes that are approaching infinite slopes there, these are approaching zero slopes here. So it's exactly the opposite. Domain all real numbers, range minus pi halves and pi halves, not inclusive, because it can't ever reach here or here. And that's all. That's all you get. Minus pi halves and pi halves for cosine 0 to pi. That's all you can have. All right. Any questions? Do these make sense? Okay. Let's then do example 3. Let's find the exact value of these 3 functions. Okay? How do you guess I might be about to suggest you do this? Second?
Set it equal to
Theta. I like it. Okay. Now write the equivalent equation to that. Cosine theta is equal to root 2 over 2. What angle theta, but now you have to restrict it, in between what? What angle theta in between what two endpoints? Dealing with cosine now. Picture the cosine function. 0 to pi. It has to be between 0 to pi. So what angle between 0 and pi will give you a cosine of root 2 over 2? Theta must be, anyone say it? Thought I heard it. Square root of 2 over 2. Wait, I'm sorry. I'm giving the wrong answer. That was that answer. Okay, I couldn't hear what you said. What did you say? Pi over 4, is that what you said? Yes, that's it, pi fourths. Pi fourths, the cosine of pi fourths is root 2 over 2. We know that. The sine of pi fourths is root 2 over 2. Yeah, we know that. Okay. So that is the angle. That's in between 0 and pi, so that's it. All right, how about arctangent of 0? How would you approach that one? Theta equal to theta, or whatever your favorite angle happens to be. And then rewrite this to read tangent theta is equal to 0. Okay? And what are our angle restrictions here for theta? It's what? Pi over 2 to pi, negative pi over 2 to pi over 2, okay? But you can't have either one of those because those are horizontal asymptotes, okay? So, what angle would give you the tangent of what angle would be 0? Pretty easy one. 0, excellent, okay. Theta equals 0. Are we almost out of time, or are people just zipping early?
Yeah, we got 1 minute.
1 minute. Let's see if we can get this last one. How would you start it?
Theta equal to theta.
Theta equal to theta. Then you'd rewrite it as tangent theta equal -1. And what angle theta? When you take a tangent of it, and now you have to stay between what two angles? Negative pi halves to pi halves. And where would you find a tangent there to be -1? Say again?
Would not be over, so would not be over like negative pi half, so it would be d.
Oh, D and E, is that what you said? Do not resuscitate? No, that's something else. Okay. No, this remember tangent can be all real numbers. Okay, so this -1 perfectly fine there. The theta can be between -pi-half and pi-half, but it's still -1 z in there. What would that be? Pretty easy one. One that's already on the board somewhere. I actually gave it away a few minutes ago when I said,
Square root 2 over 2.
okay, that is the cosine. What is the angle for that? Pi fourths, but now it's a minus pi fourths. So well, not exactly the same, minus pi fourths. Because sine and cosine are the same at the quarter pi's, right? So therefore the tangent would be plus or minus 1. Plus on this side, minus on that side. I said it backwards. Okay. All right. I think y'all know your homework exercises. I hope you do since you're leaving. Okay, so we'll pick up from there and do, that was example 3. And there is a checkpoint, so please do the checkpoint. We'll pick up and do example 4 next time. Okay? Homework exercises for those still hanging around to here will be any of the odds 5 through 17. They're all at Calc Chat. 5's at Calc View. Do 19, it's a Calc Chat. Do any of the odds, let's see, we have it done on calculator. We'll stop right there. Okay, good deal. All right, for any who came in late, I'm not going to be on the Birmingham campus tomorrow, at least early in the morning. I'll be here because I'm making up a class. Yes, ma'am. Yeah. Yeah, it has something to do with trig somewhere. Yeah.
Okay, can we just write about it or relate it to the topic, another topic?
No, say again.
Do we relate it to another topic or just write on it?
No, yeah, right. It could be a person, a theory, practical application, anything.
Okay, and you just write on it and then get more sources from the book?
No, yeah, you can't use, the book may give you ideas, but you have to get your sources outside the book. Library or...
So we could just pick like radians or degrees?
What's that?
So we could just do like radians and degree and then you write on it?
Yeah, that would be fine.
Okay.
Yeah.
Okay, I just wanted to...
Okay.